Okay, we're going to do two applications first, two examples of two applications. So that is 2 times 2, 4 examples we're going to do in total. And then we're going to go into 3 by 3 systems of equations. So this is an application I actually use. Um, let's say, so let's make a problem. This is a story problem, but it is actually a problem that I use. Um, let's say I have 33 problems, 33 problems, and I want to assign points to the problems for a test so that the total number of points add up to 65 points. 65 points. Okay. Um, if I do a 2 points each, then that's going to exceed 33 times 2 is 66. So I cannot really make 2 points each one of those 33 problems, because if each problem was if each problem was 2 points, then we would end up with 66 points rather. But I want to end up with 65 points. So there's a test I want to build. I already have 33 problems that I want to put in the test. I want the total number of points for the test to be 65 points. How do we go about this? Some points cannot be 2 points. Some points have to be 1 point instead of 2 points. The question is, how many should we do that? How many problems should be 2 points and how many problems should be 1 point? And the reason why I want to do that is because if every problem was 2 points, that will exceed the number of total points I want to have for the test. If each problem is only 1 point, that is not enough. Okay, so this is a typical kind of 2 by 2 system of equations um, problem, and this is one way to go about it. Let x be the number of 1 point problems. Okay. Let y be the number of 2 point problems. I want to figure out how many problems should be 2 points and how many problems should be 1 point. The first thing we do is assign variables to the quantities that we are looking for. So x is the number of 1 point problems, while y is the number of 2 point problems. They have to add up to 33. So now we have this equation, x plus y equals 33. That's the number of problems, 1 point problems, 2 point problems. They have to add up to 33. The total number of points should be 65. Now, how do we figure out the points? Well, each problem that is 1 point is worth 1 point, so we do 1 times x. That's the number of points coming out of those problems. And the y problems are the ones that are 2 points each. So we multiply each one by 2. Yeah. So we have the number of points from the problems that are worth 1 point, and the number of points from the problems that are worth 2 points each. So we have a system of equations, 1x plus 1y. We don't write the 1. Here I exaggerated a little bit to emphasize that these are the number of points. So the total number of problems is 33. The total number of points is 65. So here's our system of equations. And then we solve this system. We can subtract this equation minus that equation. So subtract. Again, this equation minus that equation. X minus x is no x. 2y minus y, y. And then 65 minus 33 is, well, 5 minus 3 is 2. 6 minus 3, 3. So that means we have to have 32, because y is the number of 2-point problems, 32 problems that are 2 points, and X would have to be 1. And you're probably thinking, well, I could have done that without a system of equations. Yes, we could have done that without a system of equations, but in the next example, it won't be so easy to do that. Because you probably thought, well, if I just double it, I get 66. So that means one problem has to be 1 point, and all the other 32 have to be 2 points for this to work. Okay, so, but let's write down the answer. So we need, that's an E, we need 32 problems, 32 2-point problems, and one 1-point point problem. Okay. That was our first example, and we probably don't even need a system of equations to solve that problem. Let's say we have 28 problems this time. 28 problems total. And I want all the problems to be worth 65 points. Okay. So if each problem is 1 point, that's too little. We want to end up with 65 points. If each problem is 2 points, then 28 times 2 is 56, still too little. If we do 3 points per problem, 3 times 28, I believe is 84. 8 times 3 is 24, we carry 2. 3 times 2, let me just do the multiplication. 28 times 3, 84, yep, 84. So that means that's too much. So I cannot make each one of those problems 2 points, too little. 1 point is even less. 3 points is too much. So let's say we want some problems to be 2 points and some problems to be 3 points. So which one of each do we have? Okay, so let X be the 2-point problems. Actually, be the number of the number of 2-point problems. I wonder if I did that here. Yeah, I did that here, the number of. Okay, and then let Y be the number of 3-point problems. Sometimes we get really lazy and we don't write this down. Technically, we should write it down every time we do a story problem like this, because we want to define what our variables are from the beginning. Okay, so together, they should add up to 28 problems. We have 28 problems. Some of them are going to be 2 points. Some of them are going to be 3 points. We don't know how many of each. And yes, you can probably say, well, can I make a table? You know, I can do 2. If all of them are 2 points, that's too few. If 27 are 2 points and then 1 is 3 points, then we can figure that out. You know, the total, which is not going to be 65 points. And then you can go down one by one, you know, 26 and 2 and 25 and 3 and so forth. So that's one way to go about it. You can just, you know, try and check and see which one works. But this is a more direct approach. We can simply get the answer at once. So X plus Y, the number of problems that are 2 points plus the number of problems that are 3 points, all of them together should add up to 28 problems. Now, how do we compute the points? Okay, and that's why we have to write this down so we remember. X is the number of 2-point problems. So every X is worth 2 points. We multiply by 2 to get the number of points coming from the problems from this X. Y represents the number of problems that are 3 points. So the points coming from this those y problems will be 3y. So 2 points per x problem, 3 points per y problem equals 65 total points, and we have x plus y number of problems. Okay, I'm going to multiply by 2 times 2, 2x plus 2y equals 56, and then we're going to subtract. Subtract. So 2x minus 2x is no x, 3y minus 2y, y, 15 minus, we borrow 1, 15 minus 6, 9. See, that isn't so obvious anymore. So we need 9 problems that are, and that's why we have this legend here, that because it tells us what y represents. 9 problems that are 3-pointers. And then once we have that, we can figure out the x value. X will have to be, well, if y is 9, x has to be 19. 19 plus 9 equals 28. Okay, so the solution to the problem is 9 problems should be 3 points each, and 19 problems should be 2 points each. By the way, before I wrote the answer, I should have probably double checked. So if we have 19 problems, 2 points each, that is 38 points from those 19 problems. 9 problems, 3 points each, 27 total points coming from those 9 problems. 8 plus 7, 15. We carry 1. Sure enough, we get 65 total points. So, which is what we wanted. And 19 plus 9, just the number of problems, is 28. And we started out with 28 problems. And that's actually what I do. I write out, when I'm doing my tests, I write out all the problems that I think are important. And I don't keep track of how many. I just keep writing and writing problems until I finish. You know, sometimes I end up with 28 problems. Sometimes I end up with fewer, sometimes with more. And then I have to assign the points. So this is literally what I do. I was laughing one day when I started doing, because I was thinking, oh, there's an application of math. I have to figure out how many problems I need to make 3 points and how many problems have to be 2 points. And this is exactly what I do. I go through this process. Sometimes when a problem is particularly important, I assign it 3 points. No, rather 4 points. You know, sometimes one problem is worth much more than the others, I think. That's a matter of judgment. So for instance, a story problem might be worth more than the other problems. And then what I do is reduce the number of problems and accordingly reduce the number of points. But it still boils down to the same kind of setup. Yeah. Okay. Let's talk about velocities or speeds. Yeah, speeds. Okay. So speed, of course, is relative. Relative to where we are. So for instance, I can ask the question, is this penny moving? This penny here, that penny. Is that moving? And you can say, well, it looks like it's not moving. Yeah, not moving relative to the desk, but the earth is rotating around. So we're actually moving, you know, at a high speed based on the rotation of the earth. But let's stay with more simple examples. If this is a typical example, you know, and I think this is an old example, I didn't come up with it. If somebody throws a baseball, you know, there's a baseball, this is a person, a stick man, and then that throws a baseball forward. I cannot throw too fast. I'm not very good at sports. Um, so I can probably throw, I'm going to guess, um, 20 miles per hour. And I'm only guessing. I have no idea how fast I can throw a baseball, but that seems reasonably safe, I think. 20 miles per hour, I can throw a baseball. So when I throw it, well, it doesn't have to be me, any person. When they throw the baseball, how fast is the ball going forward? Well, 20 miles per hour. Okay. What if you are on this is not very safe, so don't do it, but let's say you are in a pickup truck, on the bed of a pickup truck there. And so the person, the bed is down here, so the legs, and then you're here, and you're throwing the ball forward, same ball and same everything, the same person, and assume that, again, this is not safe, so don't do it. This is just an experiment. Let's say that the truck is going forward at 30 miles per hour. And then you're here, and you throw the ball forward, and you can throw, I hope this is not an insult, but so that's why I say me, because I don't know if this is too much or too little. So I think this is little, but that's okay. I cannot probably throw any faster than that. But anyway, I don't know. I have no idea of what a normal person can throw, the velocity of a normal person. But let's say 20 miles per hour. If the pickup truck is going at 30 miles per hour, and while the truck is going forward, if we throw the baseball forward, how fast is the ball gonna go? And let's assume there's no wind and very little air, so that there's not a lot of air resistance. So how fast, again, is the ball gonna go? Well, it turns out that the velocity of the ball after I throw it will be the velocity that I can throw at, which would be 20 miles per hour, we assume, plus the velocity of the pickup truck. So the ball will go at 30 miles per hour plus 20 miles per hour. So the ball will actually go at 50 miles per hour. So the velocity of the truck adds to the velocity of the person throwing the ball, and that is the net velocity or speed of the ball. It is going at 50 miles per hour. It goes much faster. That's why, when you are throwing an object, you have an advantage if you are running in the direction of the throw, because if you are running in that direction, it is like a pickup truck. Your legs are like the pickup truck. Then you add that to the velocity of your arm, your shoulder, your arm, your hand, everything. So things add up, and it's a simple addition. There's nothing fancy. There's nothing weird. There's no average. With an average of the velocities, we don't multiply the velocities. We simply add the velocities. There's many things we could do with the velocities. We could take the square root and or square them, and like the Pythagorean theorem kind of thing with the hypotenuse. Nothing like that. We simply add the two velocities, and you end up with the net velocity. Now let's do the experiment the other way. And by that, what I mean is, still in the pickup truck, don't do that, because this is very unsafe. You don't want to fall and then hurt yourself. This is just an intellectual experiment that we are doing on paper. Let's say the person throws the ball backward. The truck is going forward, and we throw the ball the other way. So the truck, assume, is going at 30 miles per hour, and you're going back, and you throw the ball backward, behind at 20 miles per hour. What is the net velocity of the ball after it leaves your hand? Well, we go 30 this way, but then we subtract 20 the other way. It is a simple subtraction. So the net velocity of the ball yeah, or the speed of ball is uh, 30 going forward. See, if you're just holding the ball on in your hand, as the truck goes forward, the ball is already going at 30 miles per hour. It's already moving. So when you throw it back, it is not moving at 30 miles per hour, it's moving at 30 miles per hour minus the velocity you are adding, but it's going back, so we're gonna subtract. So the ball is still gonna go forward at 10 miles per hour. Yeah, yeah. So I guess, and the same thing happens with any object. So if you have to, absolutely have to jump off a moving object, such as a truck, if you have to, um, this is super dangerous. Don't do it. Again, I cannot emphasize enough. Don't. This is dangerous. Don't ever move if you cannot help it from a moving object, because if you jump off, just this way, you're going to hit the ground at 30 miles per hour. You're going to actually scrape and hurt yourself badly, because 30 miles per hour is very, very fast. If you jump in forward, as if you had to jump and you're jumping forward, pushing and jumping forward towards the front, you're going to go even faster. Let's say you jump at, I don't know, 5 miles per hour forward. Well, you're going to hit the ground at 35 miles per hour. So if you had to jump off a moving object, if your life depended on it, and that was the only way to escape, you would have to jump pushing that way. I mean, pushing the truck behind you and then jumping behind the truck, because then you are going to subtract the velocity of the truck. Well, when you fall, you're going to subtract from it the velocity that you are pushing against the truck. So if you can push, at 20 miles per hour, then you're going to soften the fall. You're still going to hit the ground at a positive velocity. You're still going to roll and everything. You're going to scrape and hurt yourself, but it's better to fall at 10 miles per hour than at 30 or 35 or even more miles per hour. Yeah. So I didn't mean to bring that into the picture, but it's an application. If you absolutely have to jump, if there's a slow moving train and you have to jump off the train when the train is moving, then jump against the motion of the train. That way you're gonna, if you have to, don't do it, because again, it is dangerous to jump off of a moving object. Don't. Yeah, it's not good. That's what, in fact, they tell us the opposite. uh, Buckle down, put a seat belt. Um, the example that I've known about this is inside of a train. So then, you know, so I use a pickup truck instead, but it's the same kind of thing if you assume there's no wind. So what is the application to this? The application, which we're going to make an example of this, is very, very standard. It is really well known. Yeah. Let's say there's a boat, a fairly big boat. Yeah. So there's a boat, and it is crossing Lake Michigan. Yep. And we don't know the speed, the velocity. The boat goes at a certain velocity. That's called, so let B be the velocity of the boat in still water. Okay, and then there's a current. The water oftentimes is not still, it is moving. Like in Lake Michigan, the water on the surface is moving. It is making waves. So it is moving typically, I think, eastbound. So the water moves in one direction. So we're gonna label C. So I'm using B for boat and C for current. B, the velocity of the water current. Okay. Let's say they travel across Lake Michigan. I'm gonna guess at some point the distance is 80 miles. Okay, so boat goes, whoops, goes 80 miles um, in 5 hours with the current, with current. And the boat comes back or goes back, whichever way, same distance. Against the current, it is going to take longer. Let's say 8 miles, rather 8 hours against current. See, if you go with the current, the water current, so the water is moving along, and then the boat is on the water, and the boat has a velocity. So one adds to the other. The two velocities add up. It's exactly the same thing that is happening with the truck. If pretend the truck is the water, so the truck is moving along. If you are on the truck and you're not making any motion, well, you're going to move at the same velocity as the truck. That's the whole point, of having a vehicle. So the vehicle moves you at that velocity. If on top of that we throw an object forward, then the object is going to move at the velocity of the truck plus the velocity at which you or a person can throw the object. So we add the velocities. By the way, just a side note, um, if you crash against somebody going in the opposite direction and they're both going at 30 miles per hour, that is equivalent, the two velocities add up. That is equivalent to hitting a wall at 60 miles per hour. So it is very, very bad to crash head on. Very, very bad. I mean, any kind of crash is bad, especially a head on collision, because the velocities of the two objects add. So 30 miles per hour doesn't seem like a lot. Crash head on at 60 miles per hour, that is very dangerous. We don't, yeah, head on collisions are very, very bad because it's simple math, simple physics, the velocities add. So the same thing happens with a current. So if the water is moving along and then the boat is on the water, then the boat is going that much faster. It is going at the velocity of the current plus the velocity of the boat in still water. So the question we ask is, what are the velocity of boat and velocity of current? We're assuming that the current is going at a steady speed and the boat is also going at a steady speed. So we're idealizing the situation because, when the boat is close to the marina, it's actually going quite slowly. And then once it goes into more of the open water, then it goes at a full cruise velocity. So we're assuming that everything is ideal, that from the beginning to the end, the boat is going at as the regular velocity. Um, Somebody could say, well, that's not realistic. Perhaps, but we're going to get really close to the answer. Anyway, so the question is, how fast are they going? We don't know how fast the boat is going individually and how fast the current is going individually, but we can figure this out. Okay, so B is the velocity of the boat, C is the velocity of the current. When they go together, we add the velocities. So velocity of the boat plus velocity of the current equals 80 miles in 5 hours. Yep, 80 divided by 5, which is 16. Yep, 16 miles per hour. Against the current, well, we're still going forward because eventually we get there. It takes us way longer, 80 miles in 8 hours, which is 10 miles per hour. So with the current, we're going faster than against the current. The question is how much is each one of those? And that's an easy system of equations to solve, super, super duper easy. It's actually harder to set up the problem. Once we set up the problem, I'm just gonna copy this, 16b minus c equals 10. If we add the two equations, we end up with 2b equals 26, which means the boat is going at 13 miles per hour. The current, well, now that you know b is 13, 13 plus what number equals 16? Well, that's 3 miles per hour, which is like a walk. A normal walk, at least my walking, is about 3 miles per hour. So it's like a person walking, and the boat is going at 13 miles per hour by itself. Together, they go at 16 miles per hour. When the boat is going forward at 13 and the current is going back at 3, we net 10 mile per hour velocity, which makes sense. So the answer is that the boat goes at 13 miles per hour in still water, so with no current, and the current goes at 3 miles per hour. Yeah, so there's a constant current of 3 miles per hour. The water is moving at a walking speed. And then the boat in one direction is going to go against the water and then the other against the current. And in the other direction, the current is going to help out. So that is kind of neat. A neat example, in my opinion. Example 4. The same thing happens with planes. Let's say there is a plane. So a plane does I'm thinking 720 mile trip in 60 minutes with the wind, and in 80 minutes against the wind. It takes longer, and that is a fact. If the plane is flying and the wind goes in the same direction, then we add the two velocities. The plane actually saves, well, it saves time, and consequently, because it gets there sooner, the engines are on less amount of time, and consequently, they do save gas. Even if the engines are running at the same power, because the wind is helping with it, if the plane is going in the same direction, we're going to be in the air less time, and consequently the engines are going to run less time, and we're going to spend less fuel. If we are against the wind, we're going to spend, even if the engines again go at the same power, you know, there is a control and you just put it in that power and you keep it in that power for the duration of the trip, if you go against the wind, the wind is going to slow us down, just like the truck and the baseball, and that's going to cause us to spend more time in the trip, which means that we're going to spend more fuel. It's just a matter of spending more time. Yeah. Yeah. So the question is, how fast is the plane going, and how fast is the wind? How fast are the plane and wind individually? In miles per hour. Yeah. Okay, so you probably guess we're gonna set P to be the velocity of plane, and then we're gonna use another letter for the velocity of the wind, velocity of wind. So of course, it makes sense to use W because wind, P for plane. So we're gonna set those two. Okay. So what are the equations that we come up with? Well, together they go faster than against one and the other. So P plus W, so the velocity of the plane plus the velocity of the wind is 720 miles in 60 minutes. 720 over 60. And there's the calculator. I'm going to figure this out. So 720 divided by 60, 12 what? 12 miles per minute, because these are minutes. So these are miles per minute. So the units are preserved. These are not miles per hour. We will take care of that in a little bit. And then against the wind, so we're actually taking away the velocity of the wind from our flight, same distance. So perhaps the plane goes from one city to another city, and then the same day the plane goes back, and we're going to assume the wind is very uniform, going at a constant speed. But now it's going to take us 80 minutes to come back, because now we're going against the wind. And so 720 again, divide by 80, 9. So now we're going at 9 miles per hour. No. That's too slow. 9, that's slower. That's about bicycle speed. 9 miles per minute. If it was miles per hour, that would be too slow. Yeah. A bicycle would probably go faster than that. But we're flying, so we should go faster. Yeah. So never mind that those are minutes. We'll take care of that after we finish this. So far, let me write this again. P plus W equals 12. P minus W equals 9. Let's add the two equations together. P plus P, 2P. W plus negative W, no W. 12 plus 9, 21, which is not very nice, because then the velocity of the plane is 10.5. Divide by 2 and we get 10.5 miles per minute. So miles per minute. Let's transfer that immediately to miles per hour. So in every minute, think about that, we go 10.5 miles. 2 minutes, 21 miles. 3 minutes, 31.5, and so forth. So how many miles are we going to cover in 60 minutes, which is 1 hour? Well, we take the 10.5 miles per minute, 10.5, and then we multiply by 60 minutes. So we get 630 miles, which kind of makes sense. 630 miles per hour. So the plane goes that fast. How about the wind? Well, oh, this is interesting because we don't want to plug this number into this equation to figure out the wind. See, P is 10.5. So we gotta mind the units. 10.5 is P. How much does it need to be added to get 12? Well, 10.5 plus 1.5. Yep, 10.5 plus 1.5. I'm just doing this in my head. 10.5, so assume that is 10.5. How much does it need to get to be 12? Well, that means that this guy has to be 1.5, and that is consistent with this. If P is 10.5, how much do we need to subtract to get down to 9? Well, 1.5 does the job. So the wind is 1.5 miles per minute, and now we need to multiply that by 60 minutes. Boy, that's a lot. That's 90 miles per hour. That's a little bit, in my opinion, I don't know enough about this, but that's unrealistic because that is too fast. I mean, I just made up the problem out of the, I took the numbers sort of out of the blue. So it makes sense that the problem is not very realistic. I mean, the plane velocity, that I think that it seems realistic. This is too strong because a hurricane velocity is at least 70 miles per hour. So we're talking about hurricane velocities here, and it's rare that a plane flies through a hurricane. So that seems unrealistic. Again, because I just made up the problem out of the blue. Yeah. So that doesn't seem. I don't know. I gotta double check. But anyway, so let's write down the answer. So the plane goes at 630 miles per hour, while the wind goes at 90 miles per hour. Yep. So those are two standard, typical problems of two equations and two unknowns. Let's change gears now and do 3x3 systems of equations, which is the second little topic I wanted to include in this video. So 3x3 systems of equations. Three by three systems of equations. And we want to solve a 3x3 system of equations. I'm going to make up a problem, example 5. So I'm just going to say x, actually, I already had one ready, so I'm going to use that one. Minus y plus z equals 8. Negative x plus y plus z equals 10. X plus y minus z equals 6. And we want to solve this system of equations. Now, there is a couple methods. One method is elimination, which is preferred. The other method is substitution. So the methods that we have available at this point are elimination, substitution, or a combination of both. Yeah. Sometimes we eliminate one. For instance, here, it's very easy to eliminate the x because we can just add those two equations and eliminate the x at once. And if we add those two equations, we can eliminate the x. Now, you don't want to use the same equation more than once when we are eliminating, because then you're going to start going in a vicious circle. So we got to be careful. That can happen, and then that may lead to a solution that is the incorrect solution. So I'm going to label the equations so that we can keep track of them. All right. If we add equation 1 with equation 2, we notice that the x's are going to vanish immediately. And you're going to have 2. So this plus that is no x. Y plus y is 2y. Z plus z, 2z. 8 plus 10, 18. So 2y, let's write this down though. Add equation 1 and equation 2 together to obtain 2y plus 2z equals 18. Or if we divide this equation by 2, we end up with y plus z equals 9. Okay. If we add equation 2 with equation 3, the x's simplify immediately. Actually, and the z's simplify very quickly too, because this is negative and positive of the same, positive and negative and the same. Oh, this works out really nicely. Y plus y would be 2y, and 10 plus 6 equals 16. So add equation 2 and equation 3 together. So we end up with 2y. And it is a good idea to write down what you're doing. You may be thinking, well, all we care about is the solution. Yeah, but we want to have a systematic way of working the problem out, and we want to be able to go back and check if we did anything wrong where the problem may be. Anyway, adding those two together gives us 2y equals 16. That means that the y is equal to 8. I was not anticipating that. Let me double check the previous step. Oh, I added wrong. Sorry about this. Yeah, I didn't, for some reason, I missed this negative. It is very obvious, but I missed it. Adding those two equations together doesn't give us 2y. This is a negative y. It gives us 2z with no y. Whoopsie. Sorry about that. So the y's cancel out on this. And yeah, so we end up with 2z's equals 18. And that means that z equals 9. Boy, that's actually way faster. We got z, we got y. And now we can just find x by substituting. So that we would be using we could use a combination of elimination and substitution. Okay, so we got y equals 8, z equals 9, and x. I'm thinking if we can somehow get rid of the x, or get rid of the y and the z at once. Let's see. Or we should just simplify this minus that. That's not going to work, will it? This equation minus that equation. Now, we can just substitute the y and the z that we already obtained in the first equation. We can label this equation as equation 4. This one is equation 5. And then sub 4 and equation 5 into equation 1. We're going to substitute equation 4 and equation 5 into equation 1. So x, we don't know what x is, minus y we found it to be 8, plus 9, because z is 9, equals 8. So that is x plus 1 when we simplify those two, comma, x plus 1 equals 8. And that, of course, means that x is equal to 7. 7 plus 1 equals 8. Okay, so I'm going to finish example 5 here on the next page. So how do we write the answer? There are two ways to write the answer. You can simply say x equals 7, y equals 8, z equals 9, or we can put it as a triple, 7, 8, 9. In that order, we use the same order as the letters in the alphabet, 7, 8, 9. It has to be in that order. Any other order will be wrong. Let me make a note of that. Any other order will be wrong because we're assuming this is x, this is y, and this is z. Get used to both notations. Some teachers prefer this one, some teachers prefer that one. I am more liberal, and remember, by liberal, I don't mean as in political. Well, not necessarily. What I meant is, I don't mean politically. What I mean is, it doesn't matter to me which way you do it, but some teachers do care a lot. You got to do it this way, write the answer this way, or this way. So make sure you ask individual teachers which way they prefer. Yeah, and that is the prerogative of the teacher, I think, in my opinion. Yeah, so that is the elimination method, combined with the substitution method. Let's do another example, 6, of 3x3 systems of equations. 5x plus y plus 2z equals 1. Negative x plus 5y minus 3z equals 1. 8x minus y plus 5z equals 1. Okay. This problem is more difficult because in the previous one, it was pretty straightforward to just add equations the way they sat, the way they were. Just add them together, this one with this one, and something will turn out nicely. Now that I think about it, after the fact, if we added this one with this one, I just realized the y's will cancel, the z's will cancel, so we would end up with 14. 2x would be equal to 14. There was no need to do the substitution after all. Boy. So yeah, and then x would be 7. So we could have just added those two and get x immediately almost and be done with the problem. Now here, no matter what we add, if we add those two, nothing will cancel. If we add those two, nothing will cancel. Oh, yeah, I take that back. The y's will cancel. That's the only thing that would cancel off if we add those two. The y's will cancel. Okay, so I'm going to do that. I'm going to label this as equation 1, equation 2, and equation 3. And I want to keep track of what I'm doing. So we're going to add equation 1 plus equation 3. So 5x and 8x, 13x. Those two cancel each other out, plus 7z. Remember, I cross my z's to distinguish them from 2's. Otherwise, they may look too close as a 2. So 7z, and then 1 plus 1 equals 2. Okay, so we got an equation with x and z variable. The y is gone. Now I need another equation with x and z. That's another way to go about this. We can multiply. How about if we multiply the third equation by 5 because I want to eliminate the y using two different equations or a different pair of equations. See, we use those two to eliminate the y. I want to eliminate the y again using either those two or those two. Yeah. Although if I use those two again, I'm going to go in circles. That's not going to help us. So we need this pair or this pair, but I think I'm going to use this one because this one has a negative already, so it'll be easier to add. So I'm going to multiply equation 3 by 5. Multiply 3 by 5 to then add equation 2. Okay, so I'm going to do that in a step here. So multiply this by 5. That's going to give us 40x minus 5y plus 25z equals 5. Okay. Then we're gonna add equation 2. I'm gonna write it underneath. Negative x plus 5y minus 3z equals 1. And we're gonna add those together. We're gonna end up with 39x. See, this is way more complicated. The y's cancel off. 25 minus 3 is 22 plus 22z equals 5 plus 1, 6. Okay, I'm going to label this equation we obtained earlier as equation 4. You know, we had equation 1, 2, 3, now 4. I'm going to label this equation as equation 5. I'm going to write down equation 4 and equation 5 on a new page, just so I can keep them together. So equation 4 was 13x plus 7z equals 2 versus 39x plus 22z equals 6. Okay, and now we need to eliminate more. So I'm going to multiply this equation by 3. So it matches the 39. Multiply that equation by 3. So, and so that we can eliminate the x. 39x plus 21z equals 6. Let me double check my steps just to be sure. So 1 and 3, 13, no y, 2 and 5, 7, 1 and 1, 2. Multiply equation 3 by 5, 40, 5, 25, 5. Negative x, 5y, negative 3z, 1. Copy down equation 2. Add 49 plus negative x, 39, rather 40, plus negative x, 39. That adds to 0. 25 plus negative 3, 22. 5 plus 1, 6. 39 plus 22z equals 6. 13x plus 7z equals 2. Okay, I'm hoping we are right. Multiply by 3, 39, 21, 6, and then we can subtract. 39x minus 39x, no x. 22z minus 21z, z. And 6 minus 6, 0. That's why I was a little concerned, because I wasn't expecting a 0, and I kind of saw it coming. We should always double check our solutions before we turn in our work. So After we finish this, we're going to double check and make sure that the numbers we obtain for x, y, and z indeed satisfy those equations. Okay, so if z is 0, then we can figure out what x is. Yeah, it's going to be a fraction. If z is 0, then we have a fraction. Actually, this is what I'm going to do. Z is 0. We can substitute this 0. I'm going to label it as equation 6 because we already had equation 4 and 5. I didn't quite refer to it too much, but I don't want to confuse myself. So I'm just going to keep labeling equations with subsequent numbers. So this is equation 6. We're going to substitute equation 6, which means this z equal to 0, into equations 2 and 3. Although you could have done it 1 and 2 or 1 and 3. It doesn't matter. Just two of them into equations 2 and 3. Because then we have a nice system of equations. We have negative x plus 5y, negative x plus 5y equals 1. And then 8x minus y equals 1 also. Because if z is 0, that vanishes, and so does that. And adding or subtracting 0 does not change the rest of the equation. Okay, so now we got a new problem, which we're going to solve for by elimination. The reason why I prefer elimination is because of the fractions. There's going to be fractions, I can tell, that are going to show up. So multiply the first equation by 8. So let me label this equation as equation 7 and 8, because the last equation was 6, 7, and 8. So multiply equation 7 by 8, by the number 8. That's why I put this in parentheses, so that refers to the equation number 7 versus the number 8. So we have negative 8x plus 40y equals 8. I'm going to write down this equation to add with equation 8. So 8x minus y equals 1. Okay, so those two add together. 39 y equals 9, or y equals 9 over 39, or we can simplify with a 3 over 13. So y equals 3 over 13. It is very tempting to substitute back into one of those equations. We could, but I prefer elimination. I'm going to label this as equation 9. And we're going to eliminate now the y's, starting with equation 7 and 8. So it gets complicated because there's many parts going on here. So I'm going to multiply equation 8 by 5. Multiply equation 8 by the number 5. 40x 40x minus 5y equals 5 to add with equation 7. Boy, I'm doing the same thing over again, aren't I? No, I'm not. We found y. Now we're going to eliminate the y with equation 7. So negative x plus 5y equals 1. And then we add together 39x equals 6 So x equals 6 over 39, which is 2, when we simplify a 3, over 13. Okay, so our solution is x equals 2 over 13 for x, y, now I forgot, I believe it is 9 over 13, and z equals 0. Now, before I box it and declare that as our answer, final answer, let's double check. Okay. The first equation was 5. I'm copying the equation from here. 5 of the x's, so 5 times 2 over 13, plus y, plus 9 over 13, plus 2 z's, plus 2 times 0, that's easy, and let's pretend I don't know it is equal to y. If we don't get, rather, it is not equal to 1. If we don't get 1, though, I know something is wrong. So that is 10 over 13, 10 over 13 plus 9 over 13 equals 19 over 13. But we are supposed to obtain 1, which means that is not equal to 1, which means there is a mistake, at least one mistake, if not 3 mistakes there. Okay, let me check. Okay, it looks like my mistake is here. I copy the y value incorrectly. The y value is 3 over 13, not 9 over 13. Okay. That's so since I plug in 9 over 13 and that didn't work, I knew something was wrong. So I went back and checked, and it should be 3 over 13. That should fix the problem. Let's do it again. 5 times 2 over 13 plus 3 over 13 plus 2 times 0. Now it is 10 over 13 plus 3 over 13 plus 0, 13 over 13, which is 1. It checks. So plug in those numbers into the first equation, works. But don't be happy with that. Go back to the other 2 equations. Negative x plus 5y minus 3z should be equal to 1. Let's see if that is true. Negative x 2 over 13 plus 5 times y, so 5 of those is 15 over 13. And then z is going to be 0, so I'm just going to write it down for the record. Minus 3 times 0. And I can already see 15 13ths minus 2 13ths is 13 over 13, which is 1. So the second equation checks. The last equation should check, but let's double check. So 8 times 2 over 13 minus y minus 3 over 13 plus 5 times 0. Okay, so that's going to be 16 over 13 minus, 3 over 13 equals 13 over 13, which is 1. It checks. So that means, yes, now we can declare this as the solution. That's a 3. And remember, another way to write the solution is with a triple 2 over 13, comma, 3 over 13, comma, 0. So that's another way to write a solution. Some instructors much prefer this one. Some instructors prefer this one. Some instructors like me doesn't care or don't care. So any one of those will do. Practice this. If nothing else, the solving 3x3 systems of equations by hand. This is by hand. Don't use a graphing calculator. There's ways to use, excuse me, to solve the problem with a graphing calculator. Please don't. We want to do this by hand. And what I mean by that is that the most advanced calculator we want to use is this, just so we can multiply some big numbers, and that's it. But if nothing else, this develops the skill of being careful, systematic, and those basic two skills that are important to develop: being systematic as we go through a process, and very careful as we go through it, and troubleshooting, because we want to be able to, as in this case, where I made a mistake, go back and see where the mistake was. I value somebody who can go back and fix the mistakes more so than a person who never makes mistakes. Do I mean that? I don't know if I mean that. What I mean to say is, it is very, very important for me. I do, yeah. I don't know. I have to think about that. But it is very important not to make mistakes, but to be able to when we make the mistake, fix it correctly. I think that is a very, very important, because most of us always make mistakes. I mean, I claim I make a mistake at least once per hour, if not much more frequently than that. But the problem is not to make the mistake. The problem is not to be able to fix it. That's, I think, the problem. Anyway, with this, we will close this video.